It is Wednesday, my dudes, and time for an old man yapping. At the beginning of this week, somebody asked me to do an introduction to object-oriented programming, which is kind of a huge subject. But it's also kind of important because as somebody who's been doing object-oriented programming for decades, most of the people teaching it don't know what the fuck they're talking about, and they say really weird shit and teach people really odd things that make people go, object-oriented programming is stupid because of this and that. And I'm like, that's not even true. And one of the big ones is whenever somebody is explaining abstraction in object-oriented programming, they use these metaphors that relate to physical objects. Like they'll tell you, here's our example of class inheritance, and it's the hierarchy of animals. You've got animals, and then you've got vertebrates and invertebrates, and among the vertebrates, you've got dogs and cats. And on the dogs and cats, the dogs includes pugs and dachshunds and beagles and borzoi, and they always want to use physical objects. An object in object-oriented programming is just a collection of code and data. Object-oriented programming is just dividing your program into smaller and smaller parts. So I'm going to start all the way at the beginning. I'm going to begin all the way back at the part where we get signal. Main screen turn on. Okay, so in the beginning there is a signal, and the signal can be on or the signal can be off. It cannot be anything in between. It is either on or off. This is the foundation of all digital logic. In order to be digital, it's either on or it's off. Now, the world is analog, so how exactly you define on and off is typically with a range. And we're usually talking about an electrical current, and the electrical current could be positive voltage or it could be negative voltage, and somewhere in between them is a notion of zero voltage. So typically what we do is we define an area right around 0 volts as being off, and anything else is on. From a software sense, we have defined the number 0 as off, and literally anything else from 1 to max int or whatever, anything that is not 0 is on. So we regard this as false, and we regard all of this as true, which is why you can use if object as a null check, because a null value is 0. 0 is false. That's off. There's nothing there. And if it's anything else, then that's true. And what we do with these signals is all the way at the internal level, we have a bunch of transistors. And a transistor is fundamentally just 3 areas. You have a source, and you have a drain, and in between them there is a gate. And each of these has a lead attached to it. The source is what we call the collector, the drain is the emitter, and the one in the middle we call the base. There's typically an insulator between the base terminal and the actual gate material, and the way this works is you send power into the collector, but nothing comes out of the emitter unless you also send a small current into the base pin, which causes the gate to open. And then current can flow from the source to the drain, and you get that same current going from the collector to the emitter. And the symbol we use for a transistor, well, for an NPN transistor, there are also PNP transistors, but that is out of scope for this particular discussion. we use a symbol like this. The base pin is over to the side, and it has a little line to separate it from the collector and the emitter. The collector kind of bounces off the base to the emitter. If the base pin is off, if there's no signal in there, the collector simply doesn't go anywhere. Nothing comes out of the emitter unless the base pin is turned on. And the major thing we use transistors for is to do two specific gates. One of them is a unary gate that performs a NOT operation. And what happens is we apply power to a line that comes down to a transistor and connects to the collector pin. And it leads to the emitter pin. And the emitter pin shorts to ground. Our input signal is coming in at the base. So our input comes in at the base. We have a power supply that's coming into the base pin, and over to the side is our output. Now, when the input is on, the power shorts to ground, and there's no signal on the output. So when the input is on, the output is off. But if the input is off, then the power comes down here, and it can't go through because the gate is shut. So it goes directly to the output, and the output is on. So when the input is off, the output is on. So the output is the opposite of the input. If the input is on, the output is off. If the input is off, the output is on. Then we have the OR gate. The OR gate is a little bit different. It involves two transistors because it is a binary operation. And in this particular case, let me make this a little more clear. The emitter pins go to the output. And the collector pins come from two separate sources, the A source and the B source. And we have power connected to the base pins. Now what happens here is, with the power applied to both transistors, if the A signal is off, and the B signal is off, the A signal being off sends nothing to the output, and the B signal being off sends nothing to the output. So our output is off. But if the A signal is on, the A signal goes to the output, and our output is on. If the B signal is on, then again, the B signal goes to the output, and the output is on. If both of them are on, then again, both signals go to the output, and the output is on. And we typically read this in a series of zeros and ones. We use 0 for off and 1 for on. So the way that we would write this in a compact binary number representation is 0, 1, 1, 1. Now, I've mentioned this before on previous videos, but the important thing to get here is that using just these two operations, NOT and OR, and the concept of a signal that can be on and off, we can derive all of the functionality of a computer. And I'm going to demonstrate that by going to what we call compound logic gates. Now we're going to talk in terms of text here. So the OR gate we've just talked about. We've talked about A being off and A being on, B being off and B being on, and we have the A or B representation right there, which is 0, 1, 1, 1. So the thing is, we can also implement a number of NOT gates into this. We can use a NOT gate on the first input, A, and then we get different results. Now, this is called an A imply B gate, because if A is off and B is off, that's fine. If A is on and B is off, that's not fine. If A is on, B also has to be on. A or not B, well, that gives you the exact same thing except in reverse. B implies A. If B is on, A also has to be on. And then we have using not on both of them. Not A or not B gives us an entirely different set of stuff that's called A NAND B. If A or B, if A is on or B is on or neither of them is on, all of that's fine. But if they're both on, that's not fine. This is just the opposite of the original situation right here. Similarly, we have what's called the NOR gate, A nor B, which is the same as saying not A or B. From this, we can construct a number of additional things. Because when we want an AND gate, what we want is a situation where if A is off and B is off, then that's considered false. If A is on and B is off, also considered false. It's essentially the opposite situation here, where we need both of them to be on to get an on result. And again, we can use the NOT gates to do all of the different variations of this. To say if we've got A and B, that's just not A or not B. Not A and B, A and not B, not A and not B. And you can see that this is fundamentally just the same thing as what we already had. It's just in reverse order. Okay, you can see here that not A and not B gives us a NOR gate. So if we start at the bottom here, we can jump up one. We can go not A or not B. Well, that's exactly the same as if we go A NAND B. And you can see that when we look at all of this, we've got the 0, 0, 0, 0 running diagonally down here, and we've got a 1, 1, 1, 1 running diagonally down here. Now what these do is these effectively guarantee that mathematically we can construct any result we want. But finally, we have what we call the XOR gate. And the XOR gate is the last set of logical operations. It's if one of them is on, but not both of them. And if both of them are off, that's false. If both of them are on, that's false. Only one of them can be on for an XOR to be true. XOR is a fun one when you look at how it's constructed. I'm confusing myself trying to explain these, but the important thing is not that you need to remember this stuff, but that you need to be aware you can build all of these logic gates from nothing but nots and ors. And then we've got 6 additional things. If you look over these, there are 10 distinctive results, okay? And then down here we have the other 6 results, which is when it's always on, always A, always B, always off, always not A, and always not B. And that gives you your full 16 results. Now from these, you can construct useful circuits. And the most obvious one is the half and full adders, and also the half and full subtractors. Now, a half adder does an A XOR B to create a sum bit, which is A and B added together in a binary sense. And then A and B produces what we call the carry bit, which is how you carry the 1 to the next place in the number. Using those two things, you can do all of the work of adding 2 numbers together, but you have to cascade 2 of them in order. You have to do an A XOR B, XOR the input carry bit to get the sum. And then you have to do A XOR B and the input carry bit to get the mid-range carry bit. And then you have to do A and B or the carry midpoint bit to produce your carry out bit. All of that can be used to add numbers together in a cascade from the bottom of the number all the way up to the top of the number. And a subtractor works the same thing, except instead of A XOR B and A and B, it's a not A and B to determine whether there's a borrow bit. We still call it the carry flag, even though it's a borrow bit. And a full subtractor is cascaded the same way. It's okay if you're confused by this. You don't have to remember all of this. You don't have to understand it. We're not going to have a test on it. Okay? The important thing is to recognize there's a path from just an electrical signal through using transistors to form NOT and OR gates, through using those NOT and OR gates to construct compound logic gates, to using those compound logic gates to construct adders and subtractors, which use a carry bit to do arithmetic across an entire number, just working with one bit at a time. Now, all of that together, when you get to this point, once you can add and subtract, you can derive all of basic arithmetic. And once you can derive all of basic arithmetic, once you can build basic arithmetic out of your pieces that you've got, you can build all of mathematics. And once you can build all of mathematics, you can build all of physics. All of theoretical physics, anyway. And that allows you to write programs that do pretty much anything. These are all the pieces you need to do everything a computer can do. There are infinite possibilities. There's no limit to what's possible. It might be really huge. It might be really slow. And when we were talking about current earlier, it's not just electricity that has current. It can also be a light beam. A signal can come from a light beam, and that's an optical computer. Or it can come from a fluid. It might be water, wine, oil, vinegar, urine, whatever. And you could build a hydraulic computer. Or you could use air, and you could build a pneumatic computer. Anything that can travel from one place to another, and you can tell whether the flow is continuing, can be used as a signal in a computer. If you build a large enough one. So, because you can use water, and because you can use physical gates, there's no good reason you couldn't build a complete computer in the Stone Age. It would be huge, and it would be slow, but you could do it. This brings us to what we call imperative programming. Imperative programming is just a sequence of commands in order. Okay? And that sequence of commands just goes one right after the other. And that's your sequence is just command, 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 command. But you also have selection, which allows you to selectively skip over any number of commands and not execute them. And iteration, which allows you to skip backwards in a command set to execute the same commands over and over. Now, we're not going to have any loops in the code that I'm showing you here, but loops are important. They are a thing that exist. The thing about imperative programming is, when we look at this, what I'm implementing here is a timer. And in order to implement a timer, the first thing I do is I clear the AX register. And I do this by using an XOR command on it. When you XOR a number with itself, you always get 0. That's a neat little programming trick that actually used to run so much faster than actually setting the value to 0. Now, when you set the value to 0, the compiler automatically replaces that with an XOR, and it doesn't actually save you any time. Then I call interrupt 26, or 1A in hexadecimal. This is a BIOS facility that when AH is set to 0, AH is the high byte of the AX register. When AH is set to 0, it gets the value of the system clock as a number of clock ticks since midnight. Now, when I say clock ticks, a clock tick is a unit of time such that there are 65,536 of them in an hour. It's a weird unit. You just have to know that when you're using these facilities. Then what I do is I add to DX the value that I want to run a timer for. I want to run a timer for a certain number of ticks. So what I'm going to do is I'm going to add that to the current time, And then I'm going to save that, and I'm just going to check and see when the time the timer is supposed to end has gotten here. So what I do is I add that timer value to dx, and then I jump if the carry flag is not set. JNC is jump if no carry, if the carry flag is 0. And the +2 is just shorthand I put here for we're going to jump forward 2 instructions. So instead of running the increment CX here, which adds 1 to the CX register, we're going to jump directly to moving the high word of our time into memory and the low word of our time into memory. What comes back from this facility in the BIOS is 2 16-bit registers that form a 32-bit value. CX is the high order word and DX is the low order word. So what I'm doing is I'm storing those 2 words, but beforehand I check the carry flag, and if the carry flag is set, I carry the 1 by incrementing the high order word. Then I store them. Later, when I want to check whether the timer has expired, I get the current system time again, and the first thing I do is I check whether the high word of when it's supposed to go off has passed or not. The way I do this is to subtract the value I stored in memory from the value I just got back. And if the carry flag is set, then the value stored in memory is higher than the value I got back from the time. That sets the carry flag, and because that sets the carry flag, well, I don't want the timer to go off. But if I don't do that jump, then I subtract from the low word pointer. And again, if the current time is less than the time when the timer goes off, then we want to jump over this jump that goes to the routine where the expired timer is executed. Again, you don't have to understand all of this. The primary thing to get out of it is there's a lot of secret arcane knowledge that you need to bring in with you to write this code. It's not easy to read, it's not easy to write, and all of that stuff that I just had to explain about logic gates and how adders work and how subtractors work, all of that is necessary so you understand why we're checking the carry flag. The carry flag is the proper thing to check in this context, but if you don't understand how the underlying processor works, you're not going to know that the carry flag is what you're supposed to check. So you have to know all of this shit to get this timer to work. And on top of that, every time you want to check the timer, you have to write that code all over again. And you might make a mistake in just one place where you check the timer. And if you make a mistake in just one place where you check the timer, then when the timer malfunctions, you gotta find the one place you fucked it up. This is kind of a nightmare. And because that's a nightmare, we moved to what we call procedural code. Procedural code gives things nice, easy names that make sense. And these nice, easy names that make sense allow us to do stuff like say, okay, we're going to set the timeout. We're going to set the timeout value for the timer. And when we set the timer, we're going to say, hey, set the timer to this many ticks. And we're going to get the system time, and we're going to add the number of ticks for the timeout. And when we do that, we're going to store that. So what we'd actually do when we do this is we're going to say timeout equals set timer however long. And then when we go to check the timer, we're going to look and see whether the time has passed, okay? And we're going to check the timer, we're going to see whether it's greater than 0. If the timeout is still greater than the current system time, the timer hasn't gone off yet. But if it's less than 0, the system time has passed when the timer expires. You've undoubtedly seen the problem here. And the problem is you still still need to bring a substantial amount of understanding about how the system works in with you, or you can't use the code. This is one of the reasons that we went to structured code. There are also other problems here, like we've got a global variable. Global variables are just generally insecure. There are only so many of them. There are only so many names you can come up with. This is why you end up with absolutely terrible names like timer 47. And the check timer function, here's the fun part. Set timer lies to you. Set timer acts like you can use whatever timer variable you want to set the timer, but when you check the timer, it always uses the same global variable timeout. On top of that, this is nasty. Because we have a local variable named timeout that is passed as a parameter, that hides the global variable. Because we've got a local variable named timeout. So you can't access the global variable in here. Within this scope, the only timeout variable is the local variable. Again, you don't have to understand all this. You just have to know there's problems. There's a lot of fucking problems. Then we get to structured programming. Structured programming tries to solve this by saying, hey, none of this global variable shit. When you set the timer, pass in a pointer to the timer you're setting. Then pass the amount of time to put on the timer. Then you set the expiration value of the timer, and you copy that over into the timer variable, and you return when it's going to expire. Now you can do this either way, okay? You can do this either way. You can pass in your timer variable and just use that directly, or you can set it based on the return value. So you can actually set two timers off of this that go off at the same time. Then when you go and check the timer, you're going to send in which timer to check. Check this timer and see whether it's expired. And what you're going to return is, you're going to return how long is remaining on the timer. How much time is left on the timer. And you get either how much time is remaining if it's a positive value, or you'll get a negative value if the timer has expired. And all of this is contained within these two functions. And most of what you need to know is isolated to within those two functions. But we still have a number of problems. One of the big ones is you need to provide a timer variable. You need to provide a space where your timer is going to be stored. And you need to keep track of all of those. So what we have down here when we get to object-oriented is kind of structured programming on steroids squared. The object-oriented version of this code is much, much longer, because what we've done in object-oriented programming, there are four fundamental concepts of object-oriented programming, and I'm going to go over those momentarily. But the big part is that we're taking the data we need to run this timer and the functions that we need to run this timer, and we're wrapping them up in a timer class. We wrap them up into one little area, and then whenever we need a timer, we just say, we need a new timer. The class has fundamentally a few things that it's doing. It has a timeout, which is how long the timer is going to run. It has a current, which is how much time is left on the timer. It has what time the timer was started, and it has a Boolean value for whether it's currently running. And with this, we can create a much better and more feature-complete timer class. When you create the timer, you send in how many ticks it's going to run, and you send in whether or not to start it immediately. But you don't do the work of setting the timer immediately. Instead, you call the internal function of setting the timer. And if the start variable is set to true, then you call the start method. And the reason we're calling if set ticks is because if you set a number of ticks that's invalid, like it's less than or equal to 0, then what you end up with is a timer that never runs. We allow a tick setting of 0. You can set a timer of 0, a timer that goes off immediately, but you can't set a timer that has a negative number of ticks. So if the number of ticks is less than 0, if it's negative, then we return false. Otherwise, the timeout is the number of ticks, and we return true. The timer was successfully set. And if we're supposed to start it, and here, we don't actually have any hiding because we have a lowercase s on start here, and we have an uppercase s start on the start function. Now, when we come down here to start, things get a little bit more complex. If the timer is already running, which we do by checking the running method, and we're not supposed to restart, when you call start, you can pass in a restart value, which defaults to false, okay? If you pass in a restart value of true, then it will restart the timer. So we can actually create here public bool restart, and that doesn't need a parameter. And we can just call return start true. That's it. That'd be our restart function. The purpose of object-oriented programming is to make adding additional functionality that easy and that simple. You know what? It would be useful if we had an additional method here that would just restart the timer instead of having to call start true. You normally call start with no parameter because we have a default value of false here. What tells people that they should call it with start true? Well, nothing. So we're going to add this handy little macro function here, the restart function that just calls start true. And when we start, what we do is the immediate sanity check. If we're not restarting, and if we're already running, then no, we can't start. We're already running. We're already started. We can't restart. If the timeout is greater than 0, then the started is the current time. That's what time we started. And the current amount of time left on the timer is the timeout value. Then we set running to true, and we return running. Okay? Now, if the timeout is exactly 0, okay, it's immediately going to come back and say, no, it's not running. We're not running. It's immediately ended. Now we come down here to stop. Stop is simple. We just take our Boolean running parameter and we set it to false. That stops it. If we have a pause, things are a little bit more complicated. If we're running, stop. If we're not running, then the remaining amount of time on the timer is the current amount on the timer, and we call start, and we set the current value in the timer to the remaining amount. This is a dirty little hack to just kind of grab something that we know how it works and put it back. This is not something that you would typically want to do, but this is a pause function that has been hacked in after the fact when you already had a start function that worked and a stop function that worked, and now somebody comes to you and says, implement pause. Okay, understanding how things work, I can muck around with stuff and I can say, okay, let's start these things. Let's start all of this. Now, we already know that we're not running, okay? So when we call start, we're not running, and we've called it with no parameter, so restart is false. So we're going to come into here. If the timeout is greater than 0, started equals time, get current time. We let that happen. The current equals the original timeout, and the running value equals true. Then we return running. So what we do is we mess with cur. What we actually want cur to be is the amount that was already on the current value. So we save that in remain, we call start, and then we put the value of cur, the value of remain back into cur. Then we return whether or not it's running. If it's running, it'll come back running. If it's not running, it'll come back not running. That way it works whether we stopped or started, either way. When we check the timer, we return the timeout. How much time is on the timer? How much time was set on the timer? When we call update, and if we're running, then we check whether or not whether the current amount of time has elapsed. And we get the current time, we subtract started. We know that the current time is going to be greater than the time when it was started. So we take how much time has elapsed, subtract that from the current amount on the timer, and if the current amount of time left on the timer is less than or equal to 0, then we complete the timer. And then we return whether or not the timer is running. Complete stops the timer. Complete sets cur to 0 if we're running and stops it. If we're not running, complete does nothing. All of these functions are very small. They do very small, very basic things. And when you look at which ones actually access the internal variables, fairly few of them do. Every time we need to check whether the value of running, the Boolean value, every time we need to check the value of the running Boolean, we don't just look at the variable. We call a function that checks whether it's running. This allows us at a later point to make a more complex version of the timer that has a more complex equation for whether or not the timer is running. It could be running or not running based on very complex conditions. The purpose of all of this is that when you come in here and your boss says, hey, I want you to go into the timer and I want you to add a restart function because we don't have a function to restart the timer. Okay, how should the restart function work? Okay, well, what you're describing is just calling start true. Well, yeah, but how do you do that? Why do you do that? Just write a restart function. We wrote the restart function in just about 3 lines. And all we had to do was go, okay, we know that's just start true. The entire purpose of object-oriented programming is to make it easy for you to modify the existing code without doing a whole lot of work. And we're going to talk a little bit about this class recurring timer after I talk a little bit about inheritance. People make way too big a deal out of inheritance in object-oriented programming. Inheritance is just a way that you go, okay, I don't want to change the way my timer object works. The timer class works, and it works well. It's very well tested. It has no bugs. We've got hundreds of thousands of customers who are using the timer class. I don't want to fuck with it. But I would like to make a timer class that recurs, that starts again after it runs out. When it's complete, it starts again. Well, you do that with inheritance. You start with the timer and you say, okay, we're going to start with our recurring timer. And the first thing we're going to do is we're going to say, how many times has it run? Currently, it's run no times. So we've got our update function needs to be modified and to say that if we are currently running, we're going to do the thing. And if we have actually run out, then we want to complete that. This is actually a bug. Should be checking the running function. Now, because we call this a public override, it's going to hide the existing update function. None of that is going to happen. None of this is going to happen. And it needs to be a bool update. Ooh, I got some bugs in there. modifying this update feature, all I want to do is, if we have run down to the end of it, okay, we're going to complete with the current delta. And the reason we're completing with the current delta is because that delta needs to be subtracted from the next runtime, okay? So the started needs to be the get current time. Is that right? Plus delta, because it's going to be negative. If it's negative, it's going to be negative, so we need to add it. And anyway, if we're running, then we want to go just complete void. Yeah, it is. Okay. So when we complete, if we're running, we want to change the started, we want to change the cur, we want to increase the count, okay? We want to increase the count because we have completed once, okay? And all we do is we change started, we change cur, we understand how those internals work, okay? And then when we look at elapsed, when we talk about elapsed, we don't just want to know how much time has elapsed on this run through of the timer. We want to know the total time elapsed. So we need the timeout times the count plus the elapsed from the base class. Okay? So we're going to call back to the base elapsed, which is the total minus the remaining. Okay? And that's going to come back, and you're going to have your timeout and your count, and you're going to get a much larger elapsed value because it's going to have all of the previous times it's elapsed in it. The purpose of inheritance is to add a little bit of functionality to a lot of existing code without breaking any of the existing code for anybody that's already using it. This is the primary purpose of object-oriented programming, so you don't break shit that works. Now, there are 4 fundamental concepts of object-oriented programming: abstraction, polymorphism, inheritance, and encapsulation. Now, what polymorphism is when you have a recurring timer class, when you declare a class recurring timer, that class can be stored and passed and moved around anywhere that somebody is already using a timer class. And whenever they're using a timer class, anything that's derived from a timer class will also fit in there, and it will keep track of stuff, and most of the time it will just work exactly the way you expect it to. All of the method calls will work. You're not going to get any errors. Your program's probably not going to crash unless there's a bug in your derived class. That you might need to fix. But polymorphism allows every recurring timer to be used in the place of a timer, transparently. And the person using it doesn't need to know there's a difference. The overwhelming majority of object-oriented programming is designed to make things easier if you don't know what you're doing. So you have to know less. Because what we found with imperative programming and with procedural programming and with structured programming is that the more you expect people to remember when they're writing the code, the more they will fuck up. Now, the other thing a lot of people get wrong, I mentioned that they try to say that objects map to physical objects. That's the abstraction. The abstraction is not pretending it's a physical object, which is what a lot of people think is dumb about object-oriented programming. The abstraction is just understanding what data and what functions are necessary for your object to work and putting them into one space where they're all bundled together and they all work as one thing. Polymorphism we just kind of went over, and inheritance we just kind of covered. Inheriting one class from another class allows you to use most of the functionality of that class. If you know you're going to need most of the code in this class, don't write that code over again. Just inherit from it. And finally, there's encapsulation. And encapsulation is it's what the class is doing in the first place. Putting the data and the code that runs your object in one place, so it's just like a box. It's like all of your code in a box. And you need all of the code, so you take it all at once instead of having to remember everything that's in the box. I don't know how good a job I've done going over this. I don't know if this has been in any way helpful, but it should correct most of the misconceptions that people may have given you about object-oriented programming. There's nothing magical about object-oriented programming. It's just a series of rules you follow because it makes it easier for a large team to work on a large project for a long time. That's important if you're going to work somewhere on the same thing for years and you've got 30 people working with you on it. It's not so important when you're one guy working on your passion project at home after hours. So a lot of people that have only ever done single-person passion projects, they don't see the point of object-oriented programming. It's for groups. It's for groups and large projects. It's when somebody on the team has written a bunch of code that you don't understand the first fucking thing about. In structured and procedural and imperative programming, in all of those situations, most especially in functional programming, if you don't understand the code your teammate just wrote, chances are very good you can't make that code work, and you don't know why, and you can't do much of anything without talking to them. That's a problem if they get hit by a bus. That's a problem if they leave the company, if they retire and move to Saskatchewan or whatever the fuck. It's a problem when these people leave the team and you've got code that nobody can make work without talking to that person. And it needlessly limits your ability to replace them. It makes it much harder when you go, all of this guy's code is in functional programming. We have to hire an expert functional programmer to do this. You shouldn't have to do that. You should be able to get pretty much anybody that knows the language you're working in, hand them the class and say, you just dig through this one file and figure it out. It should be fairly easy to go through your program and to go through your classes and say, oh, I see how this object works. I see what this object does. Things should be fairly well documented. The variables should be well named. Things should be short. Things should make sense. And things should just work if at all possible. They should be able to look at most of your functions and most of your methods and just look at it and go, oh yeah, that obviously works. There's next to no code in it. And the amount of code that they actually need to look at and go, okay, I got to understand what's going on here. There should be fairly little of that. The major thing you're doing with object-oriented programming is dividing your code up into the smallest possible bits you can so less can go wrong in that code. Less code has less bugs. It's just that simple. If you've got a series of 50 10-line functions, you can go through that and you can go, okay, this one, and you're just looking at 10 lines at a time. If you've got a 500-line function, that's a fucking nightmare. The interaction among the different parts of that one function are going to be insane. You don't want to have those long functions. You want them small. You want them tight. You want to get the code that you've tested and proven to be working well into a tiny little space all by itself where, as you saw as I was going through this, I found bugs as I was going through this code because I just wrote this shit off the top of my head over the course of the day. And as I was going through, just looking at the code and reading it and saying, here's what it does, here's how it works. Oh, wait, I fucked that up. Let me fix it. When you have small functions, you can do that. When you have small methods, you can do that. When all of the methods in the class relate to the same conceptual idea, you can do that. It's pretty simple. It makes your code easier to write and easier to maintain and easier to manage, because once you're done with a class, you can stick that class off in a corner and not touch it for years. If it's tested and debugged and everything's working and nobody's fucked with it, it's going to be fine. It's still going to work. That's the primary thing that you're supposed to be avoiding with object-oriented programming, is what we call bit rot. And it isolates what tech debt you have into individual files. So you could say there's a lot of tech debt in this class. And for those that don't know what tech debt is, it's when you do something dumb, but you really need to make this work right now. Over the course of a long-term project, you're going to do that hundreds or thousands of times. And at some point, somebody has got to go through all of that code, find all the hundreds or thousands of times you did some stupid shit to get the code out the door, and fix it, and make it something that's actually working effectively. Tech debt is when you know somebody needs to go back and fix this, but you don't have time right now. That is a problem for future you. Or even worse, future other person that has my job in 2 years. Maybe it's still you. Maybe it's not. Maybe you've moved on. Maybe you've been promoted. Maybe you're on a different project. Maybe this project was canceled. Who knows? But that's the big benefit of object-oriented programming, is to work on large teams with large projects. If you don't do large projects, you don't really need it. But it's a good thing to use anyway, so you can practice it. Because even if you're just one person, writing smaller methods is a good practice to get into. It's a good habit to have. Even if you only work by yourself, using object-oriented principles and technologies and techniques is a good way to be ready when you have to go and work on a large team. And if you do all of this stuff just as a matter of course, then when you go and you work at a large corporation and they say you have to do things this way, you just go, oh, it's only a little different than what I was already doing anyway. If you don't do it as a matter of course, you go and you work for that big corporation, you go, big corporations are stupid. Why do they even do this? So the team can work more effectively together. The way you do it, you feel like the way you do stuff is the best way to do stuff, and it probably is for you. But on a large team and a large project, it's not about you. So, I don't know. That's pretty much what I have to say about that. Let me know if you have other questions. I'll try to cover them. If you're confused by something, let me know. Just do the little YouTube dance, like, comment, subscribe, all that happy horse shit. And I wish I'd done a better job on this, but I only had like 3 days to prepare. And really, it's just thrown together. I don't know. Okay, bye.